welcome to RF transceiver design course. We are discussing the oscillator design. So, in oscillator design, in last class we have seen the one port oscillator design, and we already have seen one approach that we used in RFIC, one port view of oscillator. Same can also be used, and it is widely considered in the microwave oscillator design also, and this methodology can also be used if we are going for very high frequency oscillator design like a sub terahertz frequencies. So, in that what we considered, we will consider the input impedance Z in. So, here there is a Z in input impedance, which is a input impedance when you see at the active device side. So, this is a, we can consider any transistor, and that transistor is terminated with some lossless component, and when it is terminated, it is added with terminating network. This gamma in, we need to ensure that it is providing the negative resistance, and this input matching network, if we design a combination of input reflection coefficient and gamma L such that we will get the oscillation. So, in order to get the oscillation, what we need is a, if we consider this Z in, which is Z in equal to R in A into omega, because your input impedance when you see at the active device, it has a different amplitude, it is a function of amplitude and a frequency, that is A omega plus J x in A comma omega. So, this we can write it as input impedance that we see on the active side. So, and we can write a ZL, which is equal to RL omega plus JXL omega. So, here this resistance is only function of frequency, because we are going to design the input matching network or any matching network either by using RLC circuits or by using some microstrip resonators or microstrip circuits. Any ZL that we design is going to become a function of omega. So, if we want to satisfy this condition when ZL is connected with Z in, then your Z in plus ZL, Z in A comma omega plus ZL omega should be equal to 0. So, this is a condition that we should satisfy in order to have the oscillation. So, if we consider that gamma L, if we try to represent the same thing in terms of the reflection coefficient gamma L, which is given by ZL minus Z naught by ZL plus Z naught equal to, we will write ZL omega is equal to minus Z in. So, we can write minus Z in minus Z naught divided by minus Z in plus Z naught, which eventually we can write a Z in plus Z naught, if we take a negative, by Z in minus Z naught, which is equal to 1 by gamma in. So, finally, the condition for oscillation is gamma gamma in gamma L is equal to 1. So, this is how we can consider gamma in gamma L is equal to 1, that is a condition to have a one port oscillation. Now, this is a this Z in and ZL are, it is a frequency dependent. So, in order to have a stable oscillation condition, there is a one Kurokawa identity that needs to be satisfied. What it says, Kurokawa identity, that your del del R in by del A means which is changing the amplitude with the where A is equal to A naught multiply with the del x L omega divided by del omega at omega is equal to omega naught minus del x in E by del A for A is equal to A naught del R L by del omega for omega is equal to omega naught. These should be greater than 0. So, this is a Kurokawa condition of stable oscillation, and mostly this RL del RL by del omega is 0. So, this condition, this del R in by del A function of amplitude at A is equal to A naught del XL omega by del omega, omega is equal to omega naught should be greater than 0, and we will try to see that how we can design the oscillator by using this method. So, when we try to find out the design or power, we need to make sure that our series resonator means this is here a series resonator and this is R in A. Now, if we consider this input impedance which is a negative resistance and changing with the amplitude, that resistance is changing with the amplitude, we can define it as a one function, and that function that at amplitude 0 it has a negative resistance R, and as amplitude is increasing your negative resistance is decreasing. So, we want to have a maximum power. So, in order to establish that, what we need is condition for maximum oscillator power, the operating point A naught and omega naught, we need to find the amplitude A naught and omega naught. It should be stable. So, it should satisfy the Kurokawa identity and the condition for starting the oscillation. So, now we will try to find out based on this function what are the different values. So, for condition for maximum power, if we write R in this function R in which is equal to minus R naught, it is a decreasing means resistance is increasing minus R naught A 1 minus A by A m. So, when A is equal to A m, your input resistance R in is equal to 0, and for when A is 0 it is a minus R naught. So, we need to find out the value of amplitude and the resistance for the maximum power. So, power can be given by 1 half real part of V1 I conjugate. We can write a half I1 square into I square R, I1 square into R in A, where R in can be replaced with here. So, it can be given by 1 half A square R naught 1 minus A by A m less than 0 as power is generated. Now, here if we try to find out that dP by dA differentiate with the A and equal to 0, you can get both the amplitude and the resistance R in for getting the maximum power. So, if we equate it equal to 0, maximum power occurs for A naught max which is 2/3 AM. So, at this point you will get maximum power. If you put a 2/3 AM in this equation, you will get R in A naught max which is equal to minus R naught by 3. So, this is a model that we have considered for the input resistance, and then based on this model, this A naught max that is required is 2/3 of AM and R in which is equal to minus R naught by 3. Now, we will see all the we will find out all the values input impedance, R in, X in, and is it stable or not. So, what are the operating point and stability? So, operating point is RL plus R in A naught equal to 0. So, RL which is given by R naught, because that is minus. So, here R naught 1 minus A naught by M. So, RL which is equal to R naught by 3. XL omega plus X in A naught equal to 0. So, if you write omega naught L minus 1 by omega naught C, this is a for series resonator, equal to 0. So, omega naught which is equal to 1 by under root LC. Same thing will apply to the parallel resonator as well. So, we get a condition RL and omega naught. Now, this is a stable or not. So, in order to find the stability, we will apply the Kurokawa stability condition del R in A naught by del A, del XL omega naught by del omega minus this equal to, as I told, this can be cancelled out. Resistance RL is will not change with omega, then only that is the real part of the impedance. So, that is not changing. So, if we consider this as a 0, then this condition del R in by A naught by del A, del XL omega naught by del omega should be greater than 0. So, we will one by one we will find out this should be greater than 0 and this should be greater than 0. So, del R in A naught by del A, which is equal to R naught by AM, which is greater than 0, and del XL omega naught by del omega, which omega naught equal to L plus 1 by omega naught square C, and based on this, if we put this equation, it is a 2L, that is also greater than 0. So, hence the operating point whatever we have defined, which is RL which is equal to R naught by 3, omega naught which is equal to 1 by under root LC, that is a operating point, and the amplitude that we have find out, that is a operating here, this operating point is a stable point. Now, we will put down all the steps and try to find out that how we can design a oscillator. So, these are the different design methodology. You can use different steps, various steps of the design methodology that you can use for designing the oscillator. So, you have a transistor available and which terminating network that you need to design. So, you need to know that gamma t. Now, you need to choose this gamma t such that your reflection coefficient, means your input impedance on this side is a negative Z in, or it is considered as a unstable, because while we have used the same method while designing the amplifier also, but here when you are designing oscillator, instead of the stable region you need to consider the unstable region. So, first is use a potentially unstable transistor. So, your transistor should be potentially unstable at the frequency of oscillation, and that you can ensure by designing a various topology that we already have seen, or you can choose a certain terminating network which will provide you the potential unstable transistor at your desired frequency. Then what you need is design the termination network to make gamma in which is greater than 1. So, we all, when I discussed the Smith chart, at that time I told, when we study the active component or oscillator, where your reflection coefficient might be outside the Smith chart and their reflection coefficient is greater than 1. So, series or shunt feedback can be used to increase the value of reflection coefficient gamma in. Then design the load network to resonate. So, we need to satisfy that Z in plus ZL equal to 0, and we already find out the value XL omega naught which is minus X in, and RL omega naught which is a mode of R in A is equal to 0 omega naught by 3. So, that R by 3 we already have calculated. Now, we will try to have the example based on that. So, here at steady state we have a reflection coefficient gamma L gamma in which is equal to 1. Therefore, gamma L which is 1 by gamma in, you can write this S11 means gamma L plus S21 gamma T S12 by 1 minus S22 gamma T, which is a terminating network reflection coefficient. So, you can represent the gamma L in terms of the gamma T, and the delta is given by this S11 S22 minus S12 S21. So, if you try to solve the gamma T, which is equal to 1 minus S11 gamma L by S22 minus delta gamma L equal to 1 minus gamma out. So, we can also write it down, gamma L gamma out is equal to 1. So, that we already have seen. Even gamma L gamma in is equal to 1, same thing, gamma L gamma out should be equal to 1, which prove that input and terminating networks are equivalent and oscillating simultaneously. So, for the condition that is for input matching network, same is for the terminating network. So, we will take one example. Design a transistor oscillator at 4 gigahertz using a gallium arsenide MOSFET. So, this is one transistor gallium arsenide MOSFET in a common gate configuration. So, this is connected in common gate configuration with 5 nano Henry inductor in series with the gate to increase the instability. So, here we need to have a instability. When we design the amplifier, we have tried to consider the stability. Now, additionally instability has been incorporated by connecting the 5 nano Henry inductor in series with the gate. What we need to do is choose a load network to match a 50 ohm load and an appropriate terminating network. So, what we need to design is this input matching network and terminating network. So, this can also be mentioned as a load network, because for oscillator that is a load. The scattering parameter of the transistor in a common source configuration are Z0 50 ohm, S11 is this, S12 is this, S21, and this is a S parameter. And when you try to use the inductor and use a common gate configuration, that will be converted to the S parameter, which is S11 is this. So, now S11 is changed from this to the this, S12 is this, S21 and S22. So, what we need to do is we need to find the output stability circle. So, if you based on this S parameter, you will get output stability circle CL and RL. We already have studied how CL and RL can be find out. So, based on the S parameter, you can find out the value of CL and RL. Once you have find out the CL and RL, you can denote the stable region and unstable. So, this is a what is shown here, the Smith chart, and there is a region has been shown. So, this here mention is a stable region. So, when we discuss the stability, at that time we discuss that if this is a Smith chart and this point, that is a, if this gamma L point, if gamma L point is equal to 0, this point is a stable if S11 is less than 0. This point is stable if S11 is less than 0, and this point is unstable. So, this is a for stability condition stable. So, gamma L is equal to 0 is unstable if S11 is greater than 0. So, what is S11 in our case? S11 is greater than 0, and because S11 is greater than 0, this gamma L is equal to 0 is a unstable point. So, this is a unstable point, that means this entire region is unstable and this is a stable region. So, what we are designing? We are not designing an amplifier, we are designing a oscillator. So, what we need to use when we try to find out the reflection coefficient for load, you need to keep the point in the unstable region. So, this is an unstable region and here the point has been chosen, which is a far from the stable region. We need to make sure that this gamma L will not reach to the stable region for different frequencies. That is why we choose it at very far compared to the stable region. Otherwise, we cannot have a oscillation. So, that gamma L we can choose value which is 0.59, angle of minus 104. We can find the reflection input reflection coefficient. So, what we got is a gamma L. So, gamma L will help us to design the uh, input means terminating network, and then gamma in, if you have a gamma in which you have find out. So, S11 based on that you can find out gamma in which is Z in. So, this is input reflection coefficient and based on that Z in we have find out. So, condition to have the oscillation, this will be minus R in by 3 and this will be XL should be minus X in. So, if we do that, minus 84 will be replaced with the 28 and minus J 1.9 will be replaced with plus J 1.9 at the ZS. So, now you have a gamma L and ZS point, both are there. You can design the input matching network. So, if you try to design, you can design the input matching network by L and C, or you can design the input matching network by the stub matching, or here the stub matching has been used. So, gamma L ZL has been used to design the terminating network, and this is at the source side. This is a transistor that is connected with the 5 nanohenry of inductor. Uh, then this if you tape out from the load side 50 ohm, this will generate the oscillation at 4 gigahertz. So, this is how you can also design an oscillator by just using a single transistor and designing input matching network and output matching network. It has a many application in which if you want to design a specific oscillator which has a application in RF transceiver design, this method can be used. So, this is how you can design a oscillator. Now, one of the important parameter of the oscillator is phase noise. So, we will try to discuss the phase noise. So, phase noise, first of all, what is a phase noise? If you see the digital circuits, in digital there is a jitter. So, around the zero crossing there is a jitter, and what will happen, that in reality in all our discussion what we have considered means when we consider the mixer and when we try to discuss the transceiver architecture, every time we have considered the delta function at f naught frequency. It is some value with a delta at f naught frequency, there is a delta function that we have defined. Now, that delta function is the value that we want, but in reality our oscillator has a many frequency component, and that has a that is spreaded across like this. So, instead of a single frequency f naught, there is a many other frequency which is on the side by side will also have, if you try to draw into the frequency domain. So, these frequency components are nothing but not a desired frequency component, and it is called as a phase noise in the oscillator, and that is generated due to the noise in the active components. So, if this is drawn as a logarithmic curve, means this, if we try to draw in form of a logarithmic log delta omega with the amplitude, Then with the power, it has a three components that we can identify. What are the three components? Because of its behavior, there is a one slope on the one side up to delta omega 1 by f cube, up to certain frequency delta omega 1 by f cube, that has a slope of 3. So, it is a 60 dB per decade slope. Now, if after the delta omega 1 by f cube, that has a another slope, that is a slope of the square. So, this has a 40 dB per decade slope. It is reducing by 40 dB per decade, and then after omega naught by 2q, this frequency it is going to become a constant. So, this model has been studied by Lessons. It is called a Lesson model of phase noise, and in which what he has considered that there are three frequency components that we can identify. So, here when we try to see the model of if we see the phase noise, so this is a phase noise, and it is given by this. I just want to tell that what is the unit that is widely used. This is the omega naught frequency, or let us say we write f naught because it is frequency, and after certain point delta f, that is called offset frequency. Offset, you have a certain amplitude of in the 1 hertz. So, the bandwidth of this is a 1 hertz. Let us say if you have a power of 0 dBm here, output power at f naught, if you have output power at f naught which is 0 dBm, then and if after delta f offset at 1 hertz you have a power of minus 120 dBm. So, this difference is called a dBc, dB difference with respect to carrier. So, this is the actual carrier frequency f naught, and at that f naught you have a power of 0 dBm, and after delta f offset you have a power of minus 120 dBm. So, that difference is called a dBc, and because you are considering it for 1 hertz of bandwidth, the dBc per hertz. So, what is the phase noise? If for delta f offset frequency, the phase noise is given by 120 dBc per hertz. So, this is a unit of phase noise where this delta f is important, delta f offset. So, ideally what we want is this value should be as high as possible. In reality, in ideally it should be infinity, and you should your delta f should be as small as possible. So, then it will lead to the delta function. We will discuss about the phase noise model, Lessons model in the next class. Thank you.